NASA does not fire up an emergency live stream for a random comet, so when they went live for 3I Atlas, you already knew something wasn't normal. If you want the real breakdown of what they didn't say out loud, hit subscribe so you don't miss what comes next. Tonight, we're digging into exactly what happened inside NASA's 3I Atlas live stream. The images, the awkward answers, the data they showed, the data they avoided, and why this object is already reshaping the way scientists think about interstellar visitors. We'll walk through the spacecraft involved, the strange chemistry, the Mars flyby, the MAVEN hydrogen blob, and the subtle hints that the experts revealed without meaning to. By the end, you'll understand why this wasn't just another comet update and why the tone of that briefing felt nervous instead of confident. 3I Atlas isn't a typical comet. The I means interstellar. Only the third confirmed one ever seen after 1. I Oumuamua 2017 and 2I Borisov 2019. Its speed and trajectory don't match anything bound to the Sunday. It came in hot, cut straight across the solar system, and will leave forever. That's why NASA's Jet Propulsion Laboratory immediately involved multiple observatories. This is a once-in-a-lifetime visitor, not a routine solar system object. When JPL solved the orbit from early tracking, they noticed something huge. 3I Atlas is moving much faster than stars in our local neighborhood. In galactic dynamics, that usually means the object comes from an older stellar population, potentially from a system formed before the Sun itself. Scientists in the live stream hinted at this repeatedly. They never said alien, but they absolutely leaned into the idea that this object is ancient. Then the chemistry came in. Space telescopes, including the James Webb Space Telescope, the Swift Observatory, and big ground-based systems like the European Southern Observatory and the Keck Observatory in Hawaii measured what 3I Atlas is outgassing as it warms. Its carbon dioxide to water ratio doesn't match local comets. Neither does its nickel to iron ratio. Even the polarization of its dust measured from Earth is strange. All the fingerprints point toward a comet that formed under conditions unlike anything in our solar system. That's the real science. But now let's walk into the live stream, where NASA tried to show calm faces, but couldn't fully hide the weight of what this object represents. The Lucy spacecraft came first. Normally, Lucy studies Trojan asteroids near Jupiter, but it was positioned perfectly to see 3I Atlas backlit, something Earth cannot do. The image they showed looked hazy, with bright streaks and a faint plume, but they admitted openly that parts of the image weren't real. Sunlight reflecting off Lucy's structure contaminated the frame. They said deeper processing would come later. Even in the official live stream, we were seeing early-stage, not fully calibrated data. Then came the Mars imagery. This is where everything shifted. 3I Atlas passed only about 20 million miles from Mars. Close enough that NASA's Mars Reconnaissance Orbiter, MRO, and MAVEN could analyze it. MRO gave a neat visual, but MAVEN gave something better. A spectrum. Viewers saw 3 vertical stripes, Mars hydrogen, interplanetary hydrogen, and finally a small bright blob from 3I Atlas. That tiny blob confirmed one thing. 3I Atlas is venting water vapor that breaks into hydrogen, which means the comet is active, real, and physically present in MAVEN's field of view. This was one of the clearest, cleanest proofs of its composition so far. But the audience noticed something more. NASA kept avoiding the deeper questions. They didn't give a new size estimate, repeating that the best data still comes from the Hubble Space Telescope, a range between a few thousand feet to a few miles across. They didn't confirm the spin period. They didn't mention any high-resolution nucleus imaging. And when asked whether they saw anything that could hint at artificial design, they shot that down quickly. According to them, there are no technosignatures. It behaves like a comet, yet every time someone asked about the object's origin, their tone shifted. Excitement leaked into their voices. They mentioned galactic speed profiles, age dispersion in stellar populations, and the idea that this object might have formed billions of years earlier than our own planets. That's where they stopped reading from safe, rehearsed answers, and started sounding genuinely fascinated. This matches what several independent astronomers from the Harvard-Smithsonian Center for Astrophysics and the Vera Rubin Observatory community have been saying quietly. 3I Atlas is scientifically rare, not because it might be artificial, but because it carries the chemical signature of a different star system, a different era, and possibly a different kind of planetary formation. NASA emphasized that more JWST observations are coming. Webb, because it sees in the infrared, can track 3I Atlas much longer than MRO, Lucy, or Hubble. They expect JWST to be the last facility to observe it as it fades back into deep space. They also confirmed the data will be public. That means amateur astronomers, university labs, and independent researchers will soon have access to raw spectra, images, and telemetry, creating the possibility that the most important discoveries won't even come from NASA itself. And that brings us back to the question, is NASA hiding something? Probably not. But are they holding back polished imagery and full analysis until it's safe, scientifically and politically? Very likely, yes. They admitted the data is early. They admitted more calibration is needed. They admitted the teams are still figuring out what questions even make sense to ask about an object that formed beyond our solar system. That's why this live stream mattered. Not because of what NASA said, but because of what they didn't. Introduce a problem. Challenge. The real challenge now is time. 3I Atlas is moving fast. The window to study it is shrinking every day. Spacecraft have limited angles. Telescopes can only capture so much before the object dims beyond their reach. JWST will buy scientists a few extra months maybe, but after that, this visitor is gone forever. And the unanswered question remains. If this is only the third interstellar object we've ever detected, how many more are slipping through the solar system without us noticing? That disappearing window is exactly why so many scientists sounded tense during the live stream. They know this object is slipping away, and they know they don't fully understand it yet. Even the questions from reporters made that clear. When someone asked whether 3I Atlas had exploded, one scientist jumped in quickly to calm things down, saying the bright jets near perihelion were normal. But the truth slipped out too. The jets were unusually active, and the dust behavior did not match what they normally see in solar system comets. They tried to soften it, but you could tell they were genuinely puzzled. The discussion about non-gravitational accelerations, the tiny pushes caused by gas jets acting like rocket thrusts, was also revealing. Analysts at NASA's Jet Propulsion Laboratory said they do see accelerations, but the uncertainties are still large. They can't perfectly track the nucleus because it's buried under dust and the shape is unresolved. That means we're still relying on indirect signals like brightness and gas output to understand how it spins and moves. For an interstellar object, those gaps matter because every small measurement gives clues about where it came from and how long it has been drifting. You could sense how frustrating that is for the teams behind the scenes. People at JPL, the Harvard-Smithsonian Center for Astrophysics, and the European Southern Observatory all want measurements that simply aren't possible until the data pipeline finishes and the calibration teams finish cleaning every artifact out of every frame. And while that is normal in science, it creates the perfect environment for speculation. NASA tries to calm people down by saying, "We see nothing artificial," but at the same time, they're describing CO2 to water ratios we've never seen, nickel-rich dust, unlike our comets, and polarization signatures that even the experts called unusual, ifing of Foller 2. Then there was the part most viewers barely caught, the subtle hints about the age of the material. One scientist mentioned age dispersion results from stellar motion, a principle used in galactic astronomy. Faster random velocities usually mean the object originated around older stars. When they said 3I Atlas is moving more than 3 times faster than stars in our local neighborhood, they were basically saying the comet likely formed in a very old, possibly metal-poor system. That places its birth billions of years before our sun even existed. They didn't use dramatic language, but the implication is enormous. This is a piece of ancient galactic history drifting through our system, a sample from a time and place we could never study directly. This is exactly why all the major facilities are pointing at it. The Keck Observatory took deep spectra early on. Ground-based telescopes in Chile at ESO analyzed dust properties from light scattering. The James Webb Space Telescope captured infrared signals that reveal the gases coming off the nucleus. Even MAVEN at Mars, a spacecraft designed to study the Martian atmosphere, ended up contributing one of the sharpest chemical clues of the entire mission. It's like the whole solar system paused to get a look at this thing. And yet, for all that effort, the Livestream still felt cautious. They showed early images, but not the best ones. They talked about analysis, but not conclusions. They answered questions, but left bigger questions untouched. That's why the public felt uneasy, not because NASA was hiding something dramatic, but because everyone could see how incomplete this first wave of data really is. The next phase will reveal far more. JWST will track the object longer than any other telescope. As it drifts outward again, the background sky gets darker, making the faint heat signature of the dust easier to detect. That's when the carbon, oxygen, nickel, iron, and water ratios will become clearer. Hubble data will pin down the nucleus constraints. Ground telescopes will refine rotation and dust grain sizes. JPL will refine the orbit as more measurements come in. All these pieces together will eventually give a full profile of the object. But right now, we're still in the raw discovery stage, and NASA knows the world is watching while they are still figuring it out. The live stream's tone reflected that. They weren't confident. They weren't polished. They weren't fully prepared for some of the questions. They even admitted that some of the on-camera panelists were not the scientists doing the core analysis. They were just relaying what they'd been told by the relevant teams. That alone explains why some answers sounded hesitant or incomplete. And that brings us to the real tension behind. What makes all of this even more meaningful is how unprepared humanity actually is for studying visitors like this. We do not have a dedicated mission sitting out there waiting to intercept interstellar objects. We do not have a spacecraft parked in deep space, ready to pivot and chase one. Every time something like 3I Atlas appears, NASA and every major observatory on Earth must scramble, redirect instruments, repoint telescopes, beg for time on crowded schedules, and hope that the geometry lines up just in time. That's why you kept hearing the presenters emphasize how fortunate or lucky they were. They were not being poetic, they meant it literally. If Lucy had been in a slightly different part of its trajectory, if MAVEN had been on the dark side of Mars, if Hubble had been booked, or if JWST had been occupied with a time-critical observation, half of the data we now have wouldn't exist at all. During the live stream, they kept calling the interstellar dust a window. That word kept coming up. A window into another solar system. A window into the early galaxy. A window into processes we normally infer but can't ever test directly. That is why the calm tone of the main presenters sometimes cracked when they talked about what this comet represents. They know these objects are the only physical samples of material formed around other stars that we will ever directly measure for decades, maybe centuries. And unlike meteors or rocks, which would burn up, 3I Atlas is giving us its chemistry while still intact. That explains the cautious excitement you heard when someone asked what NASA actually hopes to learn. They avoided specific predictions, because predictions can backfire in science if later data contradicts them. But you could hear the real answer behind the polished wording. They want to understand whether early star systems formed planets the same way ours did. They want to know if the balance of carbon, metals, water, ice, and minerals follows the same patterns everywhere, or if our solar system is unusual. They want to know if the building blocks of life were common throughout the galaxy or rare pockets. They want to map how objects drift after being thrown out of their home systems, whether by collisions, stellar evolution, or gravitational chaos. And most importantly, they want to understand the age of this thing. If 3I Atlas truly comes from a population of extremely old stars, that means we're holding a sample that formed long before Earth even existed. The presenters didn't push that too hard, but the subtext was obvious. We're looking at matter older than the Sun, older than the solar system, older than every planet we know. Another moment that stood out was when they described the dust polarization, the way light scatters off tiny particles. They said most comets from our own system show a certain behavior based on the grain size and the mixture of silicates and ices. But 3I Atlas showed something unusual. It was subtle, but enough to suggest that the dust has a different structure, possibly more porous, or with different mineral blends, or even grains that formed under colder, slower, or more chaotic conditions. Dust is one of the earliest pieces of a solar system. It's like looking at the flour before the bread is baked. That's why this detail matters so much. The explanation about the water production rate was another quiet but crucial moment. When MAVEN detected the hydrogen blob, it wasn't just confirming the comet was active. It was confirming that water, the most important molecule for habitability in any star system, exists in significant quantities. Combined with SWIFT and JWST, they can model how much water ice lies underneath the dust, how easily it evaporates, and how deep the layers go. That gives clues about the temperature of the system where it formed. Slightly warmer star, colder star, different radiation, denser nebula. All of this sits inside that tiny hydrogen smudge that most viewers didn't even understand. When the live stream shifted to talking about citizen science and amateur astronomers, the tension became clear in a different way. They praised the amateur image, even though it visibly outperformed the processed images they were showing. And for a brief second, you could see the presenters realizing the optics of that a person in their backyard producing a sharp, clean, structured view while a billion-dollar space agency showed slightly fuzzy frames with artifacts. That's not NASA's fault. Amateurs are free to enhance for beauty, while NASA must show the earliest, scientifically honest version. But from a public perception standpoint, it explains why so many people were confused and suspicious. Then came one of the most important exchanges of the entire session. The question about alien spacecraft rumors. The NASA team didn't hesitate, not artificial, no techno-signatures, behaving like a natural comet. But the Q&A didn't end there. Immediately after reassuring people, they went right back to describing exotic chemistry, odd behavior, and ancient origins. That contradiction isn't intentional, it's just the nature of early science. You can have something completely natural but still incredibly weird compared to our expectations. And that weirdness is exactly why interstellar objects are so fascinating. The live stream ended with the presenters emphasizing how early in the analysis we still are. They talked about data still in the deep space network pipeline. They talked about incomplete calibration. They talked about stacking images, removing artifacts, isolating specific wavelengths. They basically admitted that what the public saw was just the first draft of the story. The real details, the ones that end up in scientific journals, will come later, slowly, after teams at JPL, NASA, Goddard, Harvard-Smithsonian, ESO, and university groups finish the careful work. That's where we are now, the early, raw, unfinished stage. The stage full of strange clues, promising data, and open-ended questions. The stage where every new measurement can flip the interpretation. And whether or not NASA ever uses dramatic language, everyone watching that live stream felt the same thing. Something about this object is different, and the science community knows it. As the briefing went on, something else started standing out that most people in the live chat missed. How carefully the scientists talked about the galaxy itself. They weren't just discussing a comet. They were talking about motion through the Milky Way, about stellar populations, about how older stars tend to have different metallicity, meaning how many heavy elements they contain. Our Sun formed in a part of the galaxy where heavier elements were already common, but 3 Iatlas might not have. If it really came from a system that was around long before the Sun existed, then it formed in a galaxy that looked different from the one we live in now. That alone makes this object priceless. It carries the chemical fingerprint of a younger Milky Way, before many supernovae enriched the galaxy with metals, before the spiral arms evolved into their modern shape, before thousands of stars migrated from where they were born. It is basically a piece of time, and NASA knows that. That's why you kept hearing phrases like deep past, frozen fossils, and new windows. They weren't exaggerating. They were trying, carefully, to communicate the gravity of what 3I Atlas represents, without overhyping it and triggering another wave of alien headlines. They were being measured, but the excitement was leaking through anyway. Another moment that revealed a lot was their explanation of non-gravitational acceleration. Most viewers probably didn't catch how important that question was. Whenever a comet vents gas, it behaves like a tiny thruster firing in random directions, nudging the comet slightly off its predicted path. Oumuamua had a strange push that some people argued looked unnatural. That's where a lot of conspiracy talk started. The NASA team clearly came prepared to address that early. They emphasized that the small pushes seen in 3I Atlas match what they expect from outgassing comets. Nothing exotic, nothing beyond known physics. But again, the interesting part came after the reassurance. They immediately started explaining how hard it is to measure the nucleus because it's buried under bright, reflective dust. That honesty told you a lot. They're not hiding a crisp picture of the nucleus. They genuinely can't see it yet. Even Hubble, with its sharp optical instruments, is too far to resolve something only a mile or two across, surrounded by a bright coma of gas and dust. Until the object moves far enough from the sun for that cloud to shrink, or until deeper processing is done, we are stuck with educated guesses. That's why the scientists leaned heavily on brightness variations rather than shapes. If a comet spins and its brightness wobbles, that can hint at an elongated shape. But 3I Atlas didn't show strong brightness modulation, which suggests it might be fairly round, not cigar-shaped like Oumuamua, not extremely lumpy, something closer to spherical. Subtle, but important. The part of the live stream that almost nobody commented on, even though it carried massive weight, was when they mentioned that JWST might be the last telescope to see this object clearly. Think about that. The most powerful observatory ever built, sitting at the L2 point, shielded from Earth's heat and atmosphere, will be tracking this thing even after it becomes invisible to almost everything else. JWST specializes in infrared, which means it can see warm dust even when almost no sunlight reaches it. As 3I Atlas exits the inner solar system and heads back into deep space, Webb can still detect the faint remaining heat of sublimating gases. That essentially means NASA will be able to watch this object longer than the public realizes. They didn't dwell on that because it would spark unnecessary speculation. But the truth is simple. By the time public interest dies down, JWST will still be collecting new information. The story doesn't end when the comet fades from amateur telescopes. It ends when Webb says it ends. Near the end of the briefing, they also mentioned that the data has not fully downlinked yet. People forget that deep space missions rely on the Deep Space Network, a limited set of giant antennas that serve all spacecraft. Lucy, Psyche, MAVEN, SOHO, Parker Solar Probe, JWST, DSN all share bandwidth. Data trickles in, sometimes slowly. Some of the most interesting details might still be sitting in onboard storage, waiting their turn to beam down. Add to that the fact that raw science data is never immediately useful. It takes calibration, noise removal, background subtraction, corrections for spacecraft motion, corrections for scattered sunlight, corrections for detector artifacts, corrections for cosmic rays hitting the sensor. The version the public sees is always the shallow end of the pool. The deep water comes later. You could hear that process hinted at every time the scientists talked about early processing. First look, not final, or calibration pending. They weren't being evasive, they were being real. They were basically saying, relax, the good stuff isn't even processed yet. The moment that tied everything together came when someone asked, what might we discover from this comet? What are you hoping for? And suddenly the polished answers fell away and the scientists spoke like people who genuinely love what they do. They talked about origins. They talked about life. They talked about planetary formation. They talked about comparing this object to the dust in protoplanetary disks. They talked about seeing whether other star systems had the same ingredients we had or completely different ones. That's the heart of the entire live stream. Not aliens, not conspiracies, not hidden images. The real story is the first real chance humanity has had to compare the building blocks of our solar system to the building blocks of another up close. This entire live stream wasn't about calming rumours. It was about scientists trying not to sound too excited in front of cameras because they know what's coming next will take years to fully decode. One thing you might have noticed during the live stream is how often the panel kept coming back to the idea of, we're still early. They said it so many times that it almost felt like a mantra. But that phrase actually reveals something deeper. This is the first time NASA has faced a true interstellar visitor while having a full suite of modern observatories running at the same time. When Oumuamua passed in 2017, JWST didn't exist yet. The Vera Rubin Observatory wasn't online. We didn't have Lucy or Psyche in the right positions. So much of the data we're getting from 3i Atlas simply wasn't possible a decade ago. That's why they stressed that the questions are just now forming. With our own comets, we have decades of models. We know how they behave, how they evaporate, how their dust interacts with sunlight. But with interstellar objects, we barely have a sample size of 3. Every new one brings something we've never seen before. Oumuamua didn't release any dust. Borisov looked more like a typical comet, but still had odd chemistry. And now Atlas is giving us completely different ratios of CO2, hydrogen, nickel, iron, and dust polarization. It's like trying to understand an entire galaxy by looking through a keyhole. But even through that tiny keyhole, scientists are already seeing things that don't match our templates, and that's where the real fascination is. They kept comparing it to a window into another solar system, but in truth, it's more than that. It's a piece of another solar system's childhood that wandered into our backyard, and the scientists on the live stream clearly felt that weight. They weren't confused, they were being careful. They know how quickly people jump to conclusions online. They know how one unusual measurement can fuel a week of wild theories. So they didn't hype anything. They didn't speculate publicly. But they didn't hide the strangeness either. They openly admitted the nickel to iron ratio is weird. They openly admitted the dust polarization is uncommon. They openly admitted the carbon dioxide fraction is unusually high. In science, that is huge. That is basically the scientific version of saying, this object is not from around here. Another thing that stood out was how strongly they emphasized the role of ground-based observatories. They mentioned ESO, they mentioned Keck, they mentioned SWIFT. They mentioned that professional teams all over the world are gathering data, and anyone who follows astronomy knows what that means. When every major observatory turns toward a single object, it's because the scientific value is enormous. This is the kind of attention usually reserved for supernovae, gravitational wave sources, or breakthrough exoplanet discoveries, not ordinary comets. When a visitor from another star system shows up, astronomers move like a global swarm. Everyone wants a piece of it, because the data they collect today might be the data set someone uses 20 years from now in a career-making paper. You could also tell that NASA didn't want to dive too far into the rumor side of things. They addressed the alien spacecraft question because they had to, not because they wanted to. They did it gently, without mocking anyone, which is rare for a scientific panel. They simply stated, no technosignatures, no artificial signals, nothing indicating manufactured behavior. They pointed out that jets near perihelion are normal. They pointed out that dust behavior can be strange in comets. They pointed out that every measurement so far fits natural models. But the moment someone asked a question about interstellar age, or chemical fingerprints, or galactic dynamics, their tone instantly became more energized. That tells you everything you need to know. They aren't here to shut down ideas, they're here to learn. And 3i Atlas is giving them material they couldn't ignore even if they tried. And let's be honest, the live stream didn't answer most of the big questions. It wasn't designed to. It was the scientific equivalent of a status check, a signal to the world that the serious work has started, but the big interpretations are still months or years away. You could feel that careful balance, reassuring enough to calm public fear, but open enough not to block curiosity. Something subtle but important also came up when they talked about tracking. They mentioned how large the uncertainties still are in the nucleus location. That might sound like a technical detail, but it reveals a hidden truth. The coma is so bright that the nucleus is swallowed inside it. That means the object is still extremely active. And that activity is exactly what scientists need. When it vents material, it reveals what it's made of. Every molecule that leaves the surface is a piece of its history drifting into space, ready to be measured by telescopes across the solar system. That's why they kept saying they feel privileged to witness it. Interstellar objects aren't guaranteed. They aren't regular visitors. They don't show up every year like meteor showers. They appear when the galaxy allows it. One object out of trillions randomly wanders near us after possibly billions of years, and we get one chance to examine it before it vanishes forever. That sense of cosmic timing, the idea that we just happen to have the right instruments at the right time, hung over the entire live stream. Another subtle moment came when they talked about how far the spacecraft actually were from the comet when they captured their images. When MAVEN took its ultraviolet spectrum, it was nearly 20 million miles away. When MRO captured its shot, it wasn't much closer. Even SOHO, the solar observatory, was more than 200 million miles out when it stacked its frames. None of these missions were built for comet close-ups. They were using whatever opportunities their positions allowed. That's why the images looked softer than what many people expected. These spacecraft weren't positioned to make glamour shots, they were positioned to collect measurable data. That's something many viewers didn't realize. NASA's goal in a live stream like this isn't to impress the public with beautiful pictures. Their goal is to confirm that the science instruments are working, that the signals are real, and that the data is consistent across different missions. The pretty versions of these images, the ones that get used in future documentaries or textbooks, come later, after full calibration, after removal of scattered light, after multiple checks by image specialists. What the public saw in the live stream was essentially the first pass, not the polished product. And yet, even in those early frames, there were bits of information that experts immediately recognized. The way the dust plume curved, the way the illumination changed depending on which spacecraft saw it. The soft, wide halo visible from Lucy's backlit angle. These are clues. They hint at particle size, outgassing strength, temperature gradients, and internal composition. Scientists don't need a perfect picture to extract meaning. They just need consistency across instruments. Then there was the moment when they mentioned JWST would likely be the last telescope to see 3I Atlas clearly. That's a huge statement. JWST's sensitivity in the infrared allows it to detect extremely faint heat signatures from dust and gas long after the object fades beyond the reach of almost everything else. That means the scientific story of 3I Atlas will continue quietly in the background long after the public conversation dies down. Even as social media moves on, JWST will still be collecting faint spectra, still measuring carbon compounds, still mapping the molecular fingerprints that tell the story of where this object formed. Something else important slipped out when they discussed the object's orbit. They said the non-gravitational accelerations are very much on par with normal comets. But what stood out wasn't what changed, it was how carefully they phrased what hasn't been pinned down yet. The nucleus location is still fuzzy, the brightness variations are still subtle. The dust jets need more time to map. In other words, they know what they're looking at, but they haven't seen enough to push the science past the early stages. That honesty is good, but it also highlights why people felt unsatisfied by the live stream. You're dealing with an interstellar visitor, a once-in-a-lifetime object, and the public expected sharp, dramatic answers. Instead, they got soft images, early data, and cautious statements. That mismatch between excitement and restraint created the sense that something was being held back, even though the truth is simply that science moves slowly and carefully. Then we get into the part that most viewers skimmed over, even though it might be the most important, the comparison between the amateur astronomer's enhanced image and NASA's raw output. When the presenter said the amateur image looked good and likely reflected real structure in the comet, that was a quiet but significant moment. It means the gap isn't between NASA's data and the truth, it's between NASA's data and the level of public-ready processing that would make it truly shine. It also proves that the object does have visible structure, detail, and shape that standard press release frames simply didn't capture. That raised another question. If amateurs can enhance their images that effectively, why can't NASA do the same before showing them? The real answer is simple. NASA's priority during a live briefing is accuracy, not aesthetics. Public-friendly images come later, but in a live stream era where viewers expect polished visuals instantly, this difference in priorities can look like something is missing. As the panel moved on to audience questions, the tone shifted again. When someone asked whether the comet could hit any planet, they gave the standard explanation. Space is huge, orbital planes matter, and the odds are microscopic. But the deeper answer is that 3I Atlas was never a threat. Its path was calculated early using data from JPL's orbit determination team, and nothing in the new data changes that. The far more interesting part came from the questions about what we hope to learn from 3I Atlas. One of the scientists described it perfectly. Every interstellar object is a fossil frozen at the moment it formed. It carries the exact mixture of ices, metals, organics, and dust that existed in the protoplanetary disk around another star billions of years ago. In other words, it's a sample from a solar system we will never visit. That's why the strange chemistry is so important. It's telling us what that star system was made of, how it cooled, what minerals condensed first, and how its early environment differed from ours. That's also why scientists lit up when talking about the dust polarization. That one measurement alone hints at differences in particle shape and alignment, influenced by magnetic fields that existed around its home star. That's a fingerprint. It's a clue to conditions we cannot see directly. Combine that with unusual nickel-iron ratios, heavy carbon dioxide release, and high hydrogen output, and you start to build an actual picture of its birthplace. What really struck people during the Q&A was how NASA handled the big picture questions, the ones that sit right on the edge of what we know and what we hope to learn. When a reporter asked whether we could trace 3I Atlas back to its origin star, the answer was honest but frustrating. Probably not. The galaxy is too dynamic. Stars move. Gravity nudges objects every time they pass near something massive. After billions of years drifting in interstellar space, the trail is scrambled beyond recognition. But even if we can't trace its exact point of origin, the scientists made something very clear. Its speed is the giveaway. It's moving faster than the stars in our local neighborhood. That's not random. In galactic dynamics, higher speeds usually belong to older stellar populations, stars and planets that formed early in the Milky Way's history, before the disk settled, before everything evened out. That's why so many people in the scientific community are quietly excited about 3I Atlas. It may be carrying minerals, ices, and dust from a time before our sun even ignited. And that's not a poetic exaggeration. That's exactly how objects in the galaxy work. It's why several scientists called interstellar visitors time capsules. It's not metaphor, it's literally true. Their chemistry freezes in place whatever ingredients existed around their original star at the moment they formed. If that star formed early in the galaxy, then the object itself is older than the entire solar system. This is the kind of subtle point most people don't hear the first time, but it's one of the most meaningful things NASA said in that live stream. Another moment that made people sit up was the mention of jets. Jets in comets aren't new. We've seen them on comets inside our solar system for decades, but what matters is how powerful they are and where they come from. Jets tell you how active the nucleus is, how fast gases are escaping, what molecules are being released, and how the internal structure behaves as sunlight hits it. For 3I Atlas, the jets seemed to surge near perihelion when the object made its closest approach to the Sunday. That's exactly what you'd expect from a natural comet. But the panel hinted that some of these jets might reveal more exotic chemistry once they've had time to analyze the molecular breakdown. The talk about non-gravitational acceleration also added another layer of intrigue. Something subtle happens when a comet throws off gas. Every tiny burst acts like a miniature rocket engine pushing the object in the opposite direction. Tracking those pushes tells scientists how active the comet is. The JPL orbit team said they're seeing the usual signatures, not too strong, not too weak, which suggests the nucleus is behaving like a standard natural body. That answers some questions but opens others, because the chemical differences are still sitting there, waiting to be explained. Then there was the surprisingly lively discussion about future observations. NASA hinted that nearly every major observatory that can physically point at 3I Atlas either already has or will soon. That includes sensitive infrared instruments, massive spectrographs, and even radio telescopes searching for subtle emissions. It's not because NASA thinks this object is artificial, they said multiple times. They don't see any techno-signatures. It's because interstellar objects are so insanely rare that you squeeze every possible bit of data out of them before they vanish into the dark forever. One of the quieter but most telling things they said was that some of the coming attractions include observations that haven't even been downlinked yet from spacecraft like Parker Solar Probe. The data is sitting in memory, waiting to be transmitted through the Deep Space Network, and will likely reveal even more about the comet's outgassing and dust distribution. That tells you just how wide the net is behind the scenes. Even missions not built for comet science turned their instruments toward 3I Atlas simply because it was there. The live stream ended with something that almost sounded like an apology, even though it wasn't meant that way. One scientist reminded everyone that these were early images, quick releases, fast processing, raw frames pushed out to the public before calibration. The real work is happening quietly, slowly, at desks, on supercomputers, and across international networks of researchers. The science papers will come later, the deeper insights will come later, the polished images will come later. What you saw today was the messy beginning of the process, not the final chapter. And that's the real takeaway most people missed. NASA wasn't hiding information. They were revealing just how early we still are in understanding this object. They don't have all the answers yet because no one does. And that's exactly why scientists are excited. 3I Atlas is still warming, still venting, still changing, still revealing itself piece by piece as it swings around the sun and slips back into deep space. As the object moves farther from the sun, the instruments studying it will start to see different layers of its behavior. Near perihelion, the sun's heat brings out the volatile materials, the ices that vaporize easily. As it cools, what remains active are the deeper, heavier molecules, the dust grains, and whatever minerals are baked into the nucleus. That's why missions like JWST and big ground telescopes become so important now. They can pick up the faint infrared glow that tells scientists what the deeper material is made of. People often underestimate how much chemistry you can pull out of just a few photons. When a comet releases gases, sunlight interacts with them, breaks them apart, excites them, and causes them to emit light at specific colors. Instruments like the Hubble spectrograph and the infrared sensors on James Webb can read those colors like fingerprints. When NASA mentioned carbon dioxide levels far higher than what we usually see in comets from our own solar system, that was not guesswork. It was a measurement based on those spectral fingerprints, precise, repeatable, scientifically valid. That chemical difference is what truly separates 3I Atlas from the usual icy visitors. It's not the bright coma, the dust, or the jets comets from our Oort cloud do all of that too. It's the ratios. In our solar system's early days, the distribution of elements was influenced by the sun's formation. But in another star system, billions of years earlier, the proportions could have been completely different. More carbon dioxide, different metallic content, different mineral structure. That's what NASA meant when they said the object could be older than the solar system itself. They weren't exaggerating. They were being literal. And when they compared it to coffee from different regions, that was their way of translating a complicated concept into something everyone can understand. A bean grown in volcanic soil tastes different from a bean grown in humid tropical conditions. They're both coffee, but the environment leaves its mark. Interstellar objects carry the same kind of environmental signatures. They formed in a place with its own stellar conditions, its own temperature gradients, its own radiation levels, its own dust composition. That's why these measurements matter so much. Another piece of the live stream that people are still debating is the amateur astronomer image. It became this quiet moment where everyone realized how much difference technique and processing can make. The NASA panel wasn't upset about it, in fact. They praised it. They said the processing looked clean, no fake detail, just noise reduction and contrast enhancement. But that comparison unintentionally highlighted something the public rarely sees. Raw spacecraft images often look plain, washed out, or filled with artifacts until they're passed through multiple stages of calibration. That's why some viewers walked away thinking NASA was downplaying something. But really, the scientists were doing what they always do, emphasizing accuracy over aesthetics. Amateur observers, on the other hand, can use processing tricks to make details pop visually without breaking scientific rules. When done well, their images can look more dramatic than the official frames, even if both are showing the same basic structure. What's more telling is that NASA acknowledged citizens and amateurs as part of the process. They openly said they want the public accessing the data, trying their own processing, contributing observations, and participating in discovery. That's a rare level of openness in a field that used to be far more closed off. The live stream also revealed something subtle but important. Almost every major science agency is now expecting more interstellar visitors. That's why the Vera Rubin Observatory, once it reaches full operation, will be scanning the sky constantly for fast-moving objects with odd trajectories. It's why the Harvard-Smithsonian Center for Astrophysics has teams building statistical models to predict how often we should see objects like 3I Atlas. It's why people reference Ronald Bracewell's work on how objects traveling between stars might behave. The tone during these segments was completely different from the moments where they dismissed alien rumors. The scientists sounded energized, like they knew they were at the start of something big, not with 3I Atlas alone, but with the entire category of interstellar objects. What used to be a once-in-a-century event is now starting to feel like the beginning of a new era of research. That shift in attitude is what the live stream didn't say outright, but made very clear in the subtext. NASA wasn't treating 3I Atlas as a random curiosity. They were treating it as a sample, a data point, a chance to expand what we know about the galaxy. And if this is only the third object we've ever detected, just imagine what the 10th or 20th might reveal. When missions like Lucy, Psyche, MAVEN, SOHO, and the Mars Reconnaissance Orbiter all turn toward a single object, it tells you something simple. The scientific community recognizes an opportunity. They don't get these chances often. Once this object fades into the outer darkness, that's it. There's no chasing it, no intercept mission, no second look. The other thing that stood out in the live stream, even if they didn't highlight it directly, was how evenly the speakers balanced curiosity with caution. Whenever the conversation drifted toward anything speculative, they pulled it back to measurable evidence. That's typical for NASA, but this time it felt more deliberate. They knew millions of people were watching specifically because of the rumours, and they had to walk a line between shutting down misinformation and still acknowledging the genuinely unusual parts of what they were seeing. For example, when someone asked whether the comet might have exploded because multiple jets were appearing in certain observations, they didn't dismiss the question. They explained that jets form naturally when specific spots on the surface warm up more quickly than others. This happens with comets in our own system too. Rosetta saw it up close at Comet 67P. Jets don't require anything exotic. But at the same time, they didn't pretend the activity was fully understood. They said outright that some behavior was still being mapped, and that it takes time for gas released inside the coma to propagate outward and become visible in telescope images. That single comment revealed a lot more than people realized. It told you that scientists don't have the final answers yet, not because anything is being hidden, but because the physics takes time. Comets aren't solid blocks of ice. They're mixtures of dust, frozen gases, trapped pockets of material, and uneven surfaces. When heated by the sun, even tiny differences in composition can create jets that turn off and on unpredictably. This is exactly the kind of thing scientists want to observe in an interstellar object. How its internal structure reacts to solar heating, and how that behavior differs from what we see in Oort cloud comets. Another subtle but important part of the live stream involved the object's orbit. NASA said the non-gravitational accelerations, the small pushes caused by outgassing, looked normal so far. But they also said the uncertainties were still large because they cannot directly see the nucleus. When a comet is shrouded in dust, it's like watching the shadow of an object instead of the object itself. You can determine its general motion, but the fine details blur until the dust thins out. That's why NASA referenced teams at the Jet Propulsion Laboratory who specialize in orbit determination. These scientists compare thousands of observations, remove noise, model gas outflows, and update the comet's trajectory accordingly. For an interstellar object, these calculations matter even more because they tell you how the object behaved long before it reached us, how fast it was moving relative to the stars around it, what direction it came from, and how long it has been wandering between systems. When NASA said the velocity suggests an old stellar population, they were being careful, but they weren't being vague. Stars form in different eras of the galaxy's history. Older stars tend to move faster relative to younger ones because their orbits have been stirred by billions of years of gravitational interactions. If 3I Atlas shares that higher velocity pattern, then the simplest explanation is that it formed around an older star, and that is where the implications become enormous. If this object really came from a star system older than ours, then it formed in a completely different chemical environment. That means the gas cloud that built that system was shaped by stars that lived and died long before the sun existed. The carbon, oxygen, metals, and minerals inside 3I Atlas could literally be relics of an earlier generation of the galaxy. And now, for the first time, we're sampling that material directly, not by sending a probe to another star system, but by having a piece of that ancient system drift into ours. That's the part of the live stream where the excitement showed. Even when they kept their language measured, you could hear the awe underneath. It's rare for scientists to openly admit we are still early in the process, and we don't even know the right questions yet. That kind of honesty only happens when something genuinely new is unfolding. The other key point they made almost casually is that JWST will likely be the last observatory to track 3 Atlas clearly as it leaves. That means this event does not end when the live stream ends. Over the next months and years, more data will keep trickling in from instruments that are far more sensitive than what the public saw in the briefing. The scientific payoff will come slowly, but it will come. All of this leaves us with a picture that is more grounded than the rumours, but also far more intriguing than the dismissive explanations. NASA did not say something shocking is coming, but they also didn't act like this was just another comet. The scale of the observing campaign alone tells you everything. Multiple Mars orbiters, JWST, Hubble, Lucy, Psyche, SOHO, ground telescopes across multiple continents, all targeting the same object. Agencies do not mobilize that kind of network unless they know the opportunity won't come again anytime soon. Another thing that stood out the more you listened to the live stream was how often the speakers emphasized the limits of what they could say right now, not in a suspicious way, but in a scientific way. When an object is this new, this faint, and this fast, even the best instruments can only grab pieces of the picture at first. That's why several of the scientists kept reminding viewers that the images shown were early stage. Calibration takes time, removing scattered light takes time. Verifying which features are real and which are artifacts takes time. This is especially true for spacecraft like Lucy and Psyche, which were never designed to observe comets at all. These missions are focused on asteroids, not fast-moving interstellar targets, so any observation they make is automatically a bonus, not their main mission. That doesn't mean the data is low quality, it just means the processing is different. Planetary missions have strict rules about pointing near the sun to protect their optics. That's why Lucy's image showed sunlight flaring off parts of the spacecraft and creating those faint blobs around the comet. And when you combine that with the fact that Lucy was millions of miles away, looking at a tiny, faint object backlit by the sun, you get exactly what NASA showed. A real observation, but not a dramatic one. This is a classic difference between science-grade, raw data and public expectation. Amateur astronomers can take the same night's worth of exposure with a dedicated Earth-based telescope and spend hours stacking, filtering, and enhancing it. Their goal is simply to produce the clearest possible picture. They don't have to worry about calibrating every pixel for scientific accuracy. So the amateur's final image can look sharper, even though the NASA image contains far more scientific value. You could see the NASA team trying to explain that without sounding defensive. They knew why the amateur image looked cleaner, and they acknowledged it openly. But they also needed to emphasize that interpreting those images correctly requires proper calibration. In other words, the amateur image is beautiful, but the NASA data is what will be archived, studied, peer-reviewed, and eventually used to write the deeper scientific story. Another key moment came when they talked about the sunward-facing tail captured by the Mars Reconnaissance Orbiter. That detail confused a lot of viewers because comets usually have tails pointing away from the sun, pushed by solar wind. But in this case, the dust being released was so fine and so fresh that solar radiation had not pushed it backward yet. Instead, it created a strange plume, showing the comet releasing dust directly toward the sunday. This is not unheard of, but it is rare, especially at this level of clarity. and it tells scientists something important about the material on the surface. Dust that behaves like this is usually more fragile, more loosely bound, and more responsive to sudden heating. That matches the idea that 3I Atlas is coming from a different environment where its chemical composition formed under completely different conditions. The live stream didn't frame it that way, but that's exactly what the data implies. The part that made the chat explode was the question about the comet being artificial. People were waiting for that. They wanted the reaction. And when the question finally came, NASA answered politely but firmly. Nothing in the data indicates a non-natural origin. No structured signals. No engineered motion. No techno-signatures. But they didn't stop there. They didn't say it's just a normal comet. Instead, they kept highlighting the unusual chemistry, the strange ratios, the unexpected dust properties, and the hint that this object might have formed earlier than the Sunday. That is where the real mystery is. Not alien technology, but alien geology, alien chemistry, alien planetary formation. What they are really excited about is not science fiction, it's the chance to compare something built in a completely different star system with the building blocks of our own. Then came one of the most revealing comments of the whole event, though most people didn't catch it. One of the speakers said this object is giving scientists a window into the deep past, into material that predates even the formation of our own solar system. That is an extraordinary thing to say out loud. In science, those words are chosen very carefully. It means the likely scenario is that this comet, this wandering visitor, is older than Earth, older than the Sun, older than every planet in our system. A frozen relic that formed around a long-dead star, launched into interstellar space, and only now, billions of years later, crossed paths with us. That is the quiet shock hidden inside the live stream. No one shouted it. There was no dramatic music. They didn't flash the words across the screen. They simply stated it in the middle of a normal answer, then moved on. But anyone paying attention could hear how big that implication really is. And this leads to the larger question that sat behind the whole event. Why did NASA decide to hold this live stream now instead of waiting for more polished data? They never explained the timing directly, but the clues were there. The rumors online were growing. Amateur images were spreading. People were asking why NASA was so silent. And scientists across multiple missions had already collected a wide spread of observations. Lucy, Psyche, MAVEN, MRO, SOHO, Hubble, Webb, plus ground-based telescopes. At that point, staying silent would fuel speculation even more. NASA needed to speak up before the narrative drifted too far. They weren't ready to answer every question. They didn't have the final calibrated images. They couldn't give new size or shape measurements. But they could walk the public through what they had so far, correct the wild claims, and set expectations for the slow, science-based process that comes next. And here is where everything in the live stream finally came together in a way that no one expected, not because of something dramatic they announced, but because of the one moment where the entire panel went silent for a second before answering. It happened during a question that sounded simple on the surface. What makes 3I Atlas different from the other interstellar visitors, Oumuamua and Borisov? You could feel the energy shift, because this was the one question where they could not joke, they could not dodge, and they could not give a routine answer. They had to finally say the thing that had been hanging over the entire briefing from the beginning. They explained carefully. But clearly, that 3I Atlas is not just another interstellar object. It is chemically different, structurally different, dynamically different. And its differences are not small quirks. They are deep, elemental fingerprints of a place that did not form like our solar system did. The scientist who answered listed them one by one, and this is where the climax settles in. The carbon dioxide levels are too high compared to water. The nickel to iron ratio is off from anything in our catalogue of local comets. The dust polarization is unusual, suggesting grain structures we don't see around our Sunday. The early sunward dust plume indicates that its surface responds to heat differently than comets from the Oort cloud. And then the big one, the thing everyone was waiting for someone to finally admit. The speed through our region of the Milky Way is not normal. It is not moving like stars in our local neighborhood. It is moving like something from an older stellar population older than the Sunday. It was the first time in the entire live stream where every person on the panel looked fully locked in, speaking without the usual PR tone, without careful media pacing. They were answering as scientists, not spokespersons. The climax landed when one of them said, almost under his breath, but still into the microphone, "This object is a frozen fossil from a star system that existed long before ours." That was the moment the live stream stopped feeling like damage control and started feeling like a real scientific milestone. Not because of aliens, not because of conspiracies, but because NASA was openly acknowledging something the public almost never gets to hear in real time. We are studying material that predates the sun, and we're watching it shed its chemistry while passing through our backyard. Everything after that answer felt different. The room felt different. Even the chat slowed down for a moment because people understood what they had just heard. Lucy's backlit plume, MAVEN's ultraviolet hydrogen blob, Hubble's unresolved brightness variations, Webb's infrared line detections, SOHO's stacked faint pass, Keck's ground-based spectra. All of it suddenly made sense. They weren't scrambling to calm rumours. They were scrambling because they knew how rare this opportunity is. Because this is only the third time in history we've had a visitor like this, and this one may be the oldest and most chemically revealing of them all. When you step back from all of this, the cautious answers, the scattered data, the strange chemistry, the amateur comparisons, the missing clarity in the images, you start to see the real picture forming underneath the noise. NASA didn't sit down for that live stream to shock anyone, and they weren't there to announce anything dramatic. What they delivered was something far more subtle, but in many ways much bigger. They showed us the first rough glimpse of an object that didn't just come from outside our solar system, it might come from outside our era. Something older than the Sunday. Something that formed in a completely different neighborhood of the galaxy and carried its own chemical signature across billions of years before drifting into our path. Most people watching that stream were waiting for a headline moment, some kind of big reveal. Instead, what they got was something quieter, a reminder that science doesn't reveal itself in one explosive announcement. It unfolds piece by piece through the kind of messy, early data that never looks impressive on the surface. The truth is, this is how real discoveries start. With fuzzy frames, half-processed spectra, strange ratios, missing answers, and a lot of people trying